Okay, so we have defined analyticity. We have looked at some properties of analytic functions. We looked at a few examples. In this lecture, we will look at what are called harmonic functions and how harmonic functions, the idea comes about naturally when we are looking at an analytic function. Yeah, so analytic functions are special, right? So they satisfy Cauchy-Riemann conditions. They for their real part and imaginary part they do, and they do so in a whole region, right? So and this gives them some very nice properties, right? So in this lecture we will see how the real part and the imaginary part, because of that satisfying Cauchy-Riemann conditions, they also individually satisfy a partial differential equation, which is called the Laplace equation, right? Which is something which we are perhaps familiar with, and it's something that we will return to later on in this course as well, right, when we are studying partial differential equations. But here we point out that an analytic function naturally gives rise to functions which satisfy the Laplace equation. So let's start with the Cauchy-Riemann conditions. We are given u and v, and so we know that dou u by dou x must be equal to dou v by dou y, and dou u by dou y must be equal to minus dou v by dou x. So if we take a second partial derivative with respect to x in the first equation and with respect to y in the second equation, we have dou squared u by dou x squared is equal to dou squared v by dou x dou y, and dou squared y by dou y squared is equal to minus dou squared v by dou y dou x. Right, so we see that the right hand side in these two equations are really the same except for a minus sign, right? Because it doesn't matter in which order you take this partial derivative. So dou squared v by dou x dou y is the same as dou squared v by dou y dou x. So when you add these two, you get dou squared u by dou x squared plus dou squared u by dou y squared equal to 0. So this is the famous Laplace equation, right? So it's also written as this nabla squared del squared u is equal to 0. Right? So it is something that we have perhaps encountered in electrostatics, or when we're looking at properties of temperature distributions and so on. Right, so if we started with the Cauchy-Riemann conditions, and we could have also taken the second partial derivative in a slightly different way. So suppose we took a second partial derivative with respect to y in the first equation and with respect to x in the second equation. So then we would have dou squared u by dou y dou x is equal to dou squared v by dou y squared, and dou squared u by dou x dou y is equal to minus dou squared v by dou x squared. If we subtract these two equations, then once again we will see that in fact even the imaginary part also satisfies the Laplace equation. Dou squared v by dou x squared plus dou squared v by dou y squared also is 0, right? So any function which satisfies the Laplace equation is called a harmonic function, right? So we have the result that an analytic function automatically gives us two harmonic functions. The real part of an analytic function and the imaginary part of an analytic function, both are harmonic functions. But it's not enough for for us to take together any two harmonic functions and then couple them together with an I, and then you cannot have an analytic function. An analytic function is more than just two harmonic functions, right? So an analytic function for sure gives you two functions which are harmonic, but it's a little more than just that, right? So harmonic functions, like we said earlier, is something we have seen in many physical contexts. They have importance, right? One is in electrostatics when we are looking at the potential phi in a charge-free region. Another is the context of temperature profile of a heat rod, right, which is in steady state, right? So we will return to partial differential equations. We will think about partial differential equations and how to solve them and all this a little bit later in this course, and then we will discuss methods to solve such differential equations and so on. But let's look at Cauchy-Riemann conditions and how harmonic functions come from analytic functions here, right? So there's one more definition which we want to uh, give here, which is that if you have two functions uh, which are harmonic in some region, and in addition to this, their first order partial derivatives satisfy the Cauchy-Riemann conditions throughout that region. So in other words, if you got your u and v from an analytic function, then you say that v of xy is said to be a harmonic conjugate of u of x comma y, right? So yeah, so u and v not only satisfy the Laplace equation individually, but there is also a relationship between the two, which is important if they have to couple together to give you an analytic function. So let's look at a few examples which pertain to this harmonic nature. So suppose we consider our favorite function f of z is equal to z squared. So this corresponds to u of x comma y, which is x squared minus y squared, and v of x comma y is equal to 2xy. Then we can immediately say that the harmonic conjugate of x squared minus y squared is 2xy, right? Of course, first of all, the statement we can make is that each of these is a harmonic function. Not only are they both individually harmonic in nature, but v is the harmonic conjugate of u, right? So this order is also important. You cannot say that u is the harmonic conjugate of v. So in fact, it's not true, because the function 2xy plus I times x squared minus y squared is not going to be analytic. You can check this by working out the Cauchy-Riemann conditions, right? So the order in which you put these terms is important. So x squared minus y squared is certainly not the harmonic conjugate of 2xy, but the harmonic conjugate of x squared minus y squared is indeed 2xy everywhere, right? So this is an entire function. Let's look at another example. So suppose we are given some function u of x comma y, right? Y cube minus 3x squared y, and we ask if it's possible to find its harmonic conjugate. In other words, if the real part of an analytic function is given to us, can we find a suitable imaginary part such that we can tag them together and make an analytic function? So this may not in general be possible. You may have functions, real functions of two variables for which which cannot just be made the real part of an analytic function, right? So it may be impossible to find a harmonic conjugate for a function, but here it is going to be possible. So let's see the technique for how to find the harmonic conjugate of this function. So what we need is to find a v such that Cauchy-Riemann conditions must hold. So dou v by dou y must be equal to dou u by dou x, but dou u by dou x is something you can work out here. Dou u by dou x is simply minus 6xy, and we also want dou v by dou x to be equal to minus dou u by dou y, and again minus dou u by dou y we can work out, so it's just minus 3y squared plus 3x squared, right? So we know what dou v by dou y is, which is minus 6xy, and we also know what dou v by dou x is, which must be equal to minus 3y squared plus 3x squared, and this is enough to work out v up to a constant. So integrating the first of these, so immediately we have v of x comma y must be minus 3x squared xy squared plus some arbitrary function of x. So we have this freedom, right? Because dou v by dou y, regardless of what phi is going to be minus 6xy, as we can check by taking the partial derivative with respect to x. Again, that's exactly what we do next. If you take if you're taken a partial derivative with respect to y, phi of x doesn't matter, right? So because dou phi by dou y is definitely 0. As far as y is concerned, phi of x is a constant. But on the other hand, now if you differentiate this with respect to x, so then we have dou v by dou x is equal to minus 3y squared plus, now we don't need a partial derivative with respect to x, it's just a full derivative, d by dx of phi of x, which we already know dou v by dou x must be equal to minus 3y squared plus 3x squared. So this 3 minus 3y squared will cancel on both sides, and we are left with d phi by dx is equal to 3x squared, which is something which is very straightforward. We can immediately solve it, and we have phi of x must be equal to x cubed plus some arbitrary constant. So therefore, the function that is, the harmonic conjugate of u of x comma y is simply minus 3x y squared plus x cubed plus some constant. So in fact, you can show that, given a function, if it has a harmonic conjugate, it's unique up to a constant, right? So you can add some arbitrary constant, but not much else, right? So in this case, the corresponding analytic function itself turns out to be quite, we can read off what it is and write it in a very compact form. So let's write it down. So f of z is y cubed minus 3x squared y plus I times minus 3x squared xy squared plus x cubed plus c, and some inspection reveals that in fact this function f of z is just I times z cubed plus c, right? So indeed it's an analytic function, and it's just a polynomial. So basically there is no dependence on z star. So indeed the partial derivative of f with respect to z star is going to be 0. So this is an example where we managed to find the harmonic conjugate of a function because the harmonic conjugate exists. There are other examples where it's not possible to find a harmonic conjugate. So we could play with this kind of take an arbitrary function u of x comma y and try to find its harmonic conjugate, right? So it should be quite straightforward to find such a function, right? So yeah, so that would happen if it's not possible to tag together u and v and together make it into an overall analytic function. So the main message from this lecture is that whenever you have an analytic function, it gives you a real part and imaginary part, which are necessarily harmonic functions, but they're also something slightly more than that. So the Cauchy-Riemann conditions also connects them in some very special way, right? So that's what this lecture is about. Thank you.